In my Structural Engineering Made Simple series, today I talk about anchor design. This is part 2 of a two-part series and focuses on anchors embedded in masonry. Please take a moment and read the disclaimer at the bottom of this page before we continue. Anchors are used in the connection of a structural member to concrete or masonry. Common applications include anchors attaching a column base plate to the foundation, shelf angles to the masonry wall or concrete structural members, and brackets to masonry walls or concrete providing support for cables, rods, and other tension structural members. Proper design of anchors requires selecting the anchor cross-section diameter, embedment length, and the spacing between anchors, following design provisions of the American Concrete Institute, ACI. This lecture focuses on connection of anchors to masonry walls. For anchor design in concrete, please see lecture 11 of my series on Structural Engineering Made Simple. These are the pertinent references used in the preparation of this video. In particular, please note the one highlighted in red, ACI 530, issue 2013. Anchor forces. Critical forces transmitted to an anchor are an axial tensile force and a shear force. These forces are computed through detailed structural analysis based on the type of application. For example, in attaching a shelf angle to a masonry, the tension and shear in the anchor can easily be obtained based on the weight W using the equations of equilibrium, the free body diagram shown in this figure. As seen in the detail below, the applied moment M can be taken approximately as W multiplied by E. This moment is balanced by a tension force in the anchor and a compression. A more accurate estimate of the moment M is done when the weight of the outstanding leg of the angle is also considered. In this case, M is equal to W times E plus QA SA over 2, where QA is 1/2 of the weight of the angle per length, unit length, S is the spacing between the anchors, A is the length of the outstanding leg of the angle. For simplicity and conservatively, M can be taken as W plus QA S times E. In any case, the tension force in the anchor, TA, is equal to the moment divided by Y. Therefore, TA is equal to W times E plus QA SA over 2 divided by Y, or conservatively as W plus QA S times E divided by Y. And the shear force is W plus 2 QA times S. As we said before, S is the anchor spacing, QA is 1/2 of the weight of the angle per foot, and A is the length of the outstanding leg of the angle. The dimension Y can be obtained based on the gauge values listed for different size angles in the AISC manual. Important considerations. Current design requirements for the installation require the anchor embedment in grouted masonry that is properly reinforced. Only anchor bolts with a diameter of 1/4 of an inch are allowed to be installed within mortar bed joints that are at least 1/2 an inch in thickness. For the purpose of application of the provisions of ACI 530, the 1/4 of an inch diameter anchor bolts are also permitted to be considered as if they are embedded in the grout. The requirements for grouted areas around the anchor and clear distances between the end of the anchor and face of masonry are provided in the ACI 530. Other pertinent documents such as BIA dated 1986 and NCMA dated 2013 provide more detailed descriptions of the required grouted areas and clear distances for brick and concrete masonry walls, respectively. Finally, please note that special provisions in design will need to be considered for anchor design in seismic areas. Please review ACI 530 for these provisions. Types of anchors. Two broad categories of anchors are used in masonry applications. These are conventional anchor bolts and proprietary anchor bolts. Conventional anchor bolts are made by steel fabricators to meet a specific project. They are also available in standard sizes of length and diameter through steel suppliers. Proprietary anchors are available through manufacturers under their brand names. These manufacturers also provide documents and often technical assistance for design. Table 1, which is in the next slide, summarizes different types of anchors within these two broad categories. The types listed for proprietary anchors are generic and are based on the underlying theory in how anchors work. Thus, anchor configuration, sizes, and lengths are specific to each manufacturer. This type of data can be obtained through each manufacturer's published materials. Now here is Table 1. Different categories of anchors in masonry applications are provided in this table. For example, notice that for conventional ones, when we use headed bolts, the ASTM A307 or the highest strength A325 types of anchors may be used. The last column of this table gives other information about the type of anchor. However, when we use a bent bar anchor, the type could be J or L or even U shape, and the material is usually ASTM A36. The other types are through bolts and plate anchors. Information about those is provided in this table. Regarding proprietary anchors, we have either expansion anchors or adhesive anchors. Again, for each type, the configuration and additional data provided. However, it is advised that you consult with the manufacturer's technical data for additional information on the material types and other data pertinent to these anchors. These figures show conventional and proprietary anchors. Conventional anchor types are shown in here, and proprietary sleeve and wedge anchors are shown in the lower figure. Please notice that the embedment length is designated as L sub B. Effective anchor cross-sectional area and effective embedment length. In conventional anchors, the effective cross-sectional area will need to consider the reduction because of anchor threading. Table 2 summarizes effective cross-sectional areas as recommended in CMA. For example, for an anchor with 1/2 an inch in diameter, the nominal area is 0.196 square inches. However, the effective area is about 70% of that and is 0.142 square inches. The effective embedment length for a conventional anchor is usually taken as 4 times the diameter or 2 inches, whichever is greater. It is noted that the embedment length LB for headed anchors is measured parallel to the anchor bolt axis from the surface of the masonry to the bolt head bearing surface, as shown in this figure. For bent anchors, the embedment length is also shown. For proprietary anchors, the information on the effective cross-sectional area and embedment length is provided in each manufacturer's product data. Anchor modes of failure and strain computation. Modes of failure considered in design of anchors in masonry are either in tension or shear. The computation of the strength is performed with consideration for these modes. ACI 530 provides information on these modes of failure and equations for strength computations. As shown in figures here, failure in tension is defined via a conical surface separated from the masonry. This surface is defined with a 45-degree angle and dimension LB, in other words, the embedment length. The figure on the left shows the headed anchor. The figure to the right shows the bent anchor. For shear, mainly the failure occurs due to breakout, as shown in the figure to the left. Another possible mode of failure is shear pry-out, as shown in the figure to the right. As shown in these figures, you notice that the critical parameter in shear strength is the anchor distance from the edge, which is designated as L sub BE. For a single anchor, the strain computation is based on the projected area for tension APT and for shear APV, each computed based on their corresponding conical critical surface as shown in these figures. Referring to these figures and knowing that the angle of the conical surface is equal to 45 degrees, APT is pi LB squared. Looking from the top, we see a circle with 2lb as a diameter. Therefore, the parameter APT is the area of this circle. Thereby, we find in the equation APT equal to pi LB squared. And from the figure for shear breakout, the parameter APV is the area of the base of a truncated cone, which is 1/2 circle with a radius equal to LBE. Therefore, APV is pi LB squared divided by 2. As indicated in ACI 530, both for tension and shear and in computing the respective projected areas, the portion of the projected area that overlaps an open cell or open head joint or that lies outside the masonry will need to be deducted from the values of APT or APV. In cases where the projected areas of adjacent anchor bolts overlap, the value of APT or APV will need to be adjusted so that no portion of masonry is included more than once. For example, for two anchors with an overlapping projected area equal to AB, the projected area of each anchor as shown in the figure is APT equal to pi LB squared minus 1/2 of AB. The deduction of 1/2 of AB is done so that no portion of the masonry is included more than once. This is to avoid overstresses in the masonry. In using the equation for APT, ACI 530 defines the effective embedment length LB as follows. For headed anchor bolts, the effective embedment is the length of the anchor bolt measured perpendicular from the masonry surface to the compression bearing surface of the anchor head. For bent bars, the effective embedment is the length of the bar measured perpendicular from the masonry surface to the compression bearing surface of the bent end, minus 1 anchor bolt diameter. Thus, in the case of bent bars, practically LB is the length of the bar measured from the surface of the masonry to the point at the end where the curve starts. Notice that the two projected areas are important parameters in computing the tensile and shear capacity of anchor bolts. The ACI 530 also permits using tests in the determination of anchor bolt strength. In that case, tests must be according to the ASTM E488 and the minimum of 5 tests will need to be conducted. The allowable anchor load values for design cannot exceed 20% of the average test results. Computation of anchor strength. The following procedure for computing the anchor bolt strength is based on ACI 530. The allowable stress design method. The allowable axial tensile load of headed anchor bolt BB is smaller of the following two values. BAB equal to 1.25 APT square root of prime sub m and BAS is 0.6 ABFY. BAB is based on the masonry breakout while BAS uses the anchor bolt yielding. In this equation, AB is the effective cross-sectional area of the anchor bolt and the prime sub S is the masonry compression strength in PSI. The allowable tensile load of an anchor with bend, BA, is the smallest of the following three values. BAB is equal to 1.25 APT square root of prime m. BAP is 0.6 F prime m EB dB plus 120 pi times LB plus EB plus dB quantity multiplied by dB. And BAS is 0.6 ABFY. BAP is based on the anchor pull-out strength. That's the middle equation. In this equation, dB is the bar diameter and EB is the projected leg extension of the bent bar anchor, measured from the inside the edge of the anchor at the bend to the farthest point of the anchor in the plane of the hook. Please take a look at that detail shown to the right. The allowable shear load of an anchor embedded in grout for either headed or bent anchors, BV, is the smallest of the following four values. BVB is 1.25 APV square root of prime sub m. BVC is 350 multiplied the fourth root of a prime sub m. BVPRY is 2 times BAB, which is 2.5 APT square root of m. And finally, BVS is 0.36 ABFY. The first equation, BVB, defines the allowable shear strength governed by masonry breakout. The second equation, BVC, is based on the masonry crushing. The third equation, BVPRY, uses the anchor pry-out. And the last equation, BVS, defines the allowable shear strength governed by steel yielding. Interaction of axial load and shear. The combined effect of the axial load and shear will need to satisfy the following inequality. The summation of the applied load divided by resistance for the axial load and shear is smaller than 1 for satisfactory design. As explained, BA and BV are applied tension and shear on the anchor respectively. The LRFD method. When using the load resistance factor design method, applicable capacity reduction factor phi and load factors are considered. The nominal axial tensile strength BAN, notice that the subscript n is used because these are nominal capacities, of a headed anchor bolt is smaller of the following two values. And the design axial strength is 5 multiplied by the smaller of the two values. BANB is 4 APT square root of prime sub m and BANS is ABFY. Again, BA and B is based on the masonry breakout strength, while the second equation, BA and S, uses the anchor bolt strength in yielding. The nominal tensile strength of an anchor with bent, BAN, is the smallest of the following three values. And the design tensile strength is of course taken as 5 multiplied by the smallest of the three. B, A, and B, the first equation is 4 APT times the square root of prime sub M. B, A, and P is 1.5 F prime sub M EBdB plus 300 multiplied by pi times LB plus EB plus DB, the product multiplied by DB, where DB is, if you remember, is the diameter of the bar. And BA and S is AB multiplied by FY. Again, the middle equation is based on the anchor pull-out strength. The nominal shear strength of an anchor embedded in grout for either headed or bent anchors, B and V, is the smallest of the following four values. The design shear strength value is 5 multiplied by the smallest of the four. The first equation, B, V, and B, is 4 APV square root of prime sub M. The second equation, B, V, and C, is 1050 times the fourth root of a prime sub M. Third equation, B, V, and P, R, Y, is 2 multiplied by BAB, which is 8 multiplied by APT, square root of prime sub M. And finally, the fourth equation, B, V, and S, is 0.6 ABFY. As explained in front of each equation, the first equation, B, V, and B, defines the shear strength governed by masonry breakout. The second equation, B, V, and C, is based on the masonry crushing. Third equation, B, V, and PRY, uses the anchor pry-out. And finally, the fourth equation, B, V, and S, defines the shear strength governed by steel yielding. Interaction of axial load and shear. The combined effect of the axial load and shear will need to satisfy the following inequality. Notice that in this interaction equation, factored load used, and in the denominator, the factored resistance are applied. As explained, BAF and BVF are factored applied tension and shear on the anchor respectively. Now, in regard to the resistance reduction factor, phi is taken as 0.9 for tension and 0.8 for shear. Let's look at an example. We are using an angle 6 by 6 by 3/4 of an inch in thickness as a shelf angle attached to a masonry reinforced grouted brick bearing wall. We have done the calculation for the forces. The tension in the anchor is 1,313 pounds and the shear is 863 pounds. If we want to use the LRFD method, because the dead load is the only load present, these values each is multiplied by a load factor of 1.4. Therefore, the factor tension is 1,838.2 pounds. Factor shear is 1,208.2 pounds. We are assuming the masonry strength of prime sub is 2,000 psi. In this problem, the anchor spacing is 2 feet. The anchors used are headed ASTM 307 with a diameter equal to 0.5 inches. Therefore, the effective area is 0.142 square inches as previously was given in a table. If we use an embedment length of 6 inches and an edge distance of 8 inches with a wall thickness equal to 12 inches, we can compute to find out whether the allowable axial tension and shear loads of the anchor are okay using the AST method, and then we can also repeat the problem with the LRFD approach and find out whether this selected angle with the embedment length and edge distance specified is okay for the design. For an A307 anchor, the yield capacity is 36,000 psi. We compute the APT based on the embedment length of 6 inches, which is 111.1 square inches, and APV based on the 8 inches of edge distance, and in this case is 100.5 square inches. Because this is a headed anchor, the allowable tensile and shear forces can be obtained based on the equations given. For the allowable tensile, we have the smaller of the two values listed, plugging the numbers in the equations, making sure that proper units are used in pounds and inches. We find out that the smaller of the two values is 3,067.2 pounds. That's the piece of A. And if you remember, there are 4 values for shear. We have to pick up the smallest of the 4. Plugging the numbers there, we found the smallest value, which is BV, is 1,840.3 pounds. Now plugging those in the equation, in the interaction equation. Now remember that the applied loads are 1,313 for tension, 863 for shear. Dividing each of those by their respective strength values, we find out the interaction value is 0.9, which is less than 1. Therefore, the design is okay if we use the allowable stress design method. Now we repeat the process using the LRFD approach. Remember that a load factor of 1.4 was applied to the loads. From the two equations for tension, we find out two values. A smaller one is 5,112 pounds. This indicates the failure of this would happen in tension with the failure of the anchor itself. In other words, the yielding, rather than with failure of concrete. And for shear, we had the 4 equations. We plug numbers there. And the smallest possible value out of the 4 is 3,067.2. Again, you notice that this corresponds to the 4th equation, which is the failure by yielding. Now, if we plug those in our interaction equation for LRFD approach, remembering that the applied loads are factored, and in the denominators, we need to apply the resistance reduction factors of 0.9 for tension and 0.8 for shear. We end up with the interaction value as 0.89, which is smaller than 1. Therefore, the design is also okay if we use the load resistance factor design method. Anchor design in masonry requires proper consideration of the pertinent tension and shear modes of failure. In situations when seismic forces are present, the design will also involve special considerations, including ductility requirements. Thank you for watching this video.